So at this time, I'd like to invite up the Martin Fleischmann Memorial Project. There's actually two presenters for this project. The first is going to be Tyler Van Houwelingen, and you're going to be joined by Bob Greenyer. I'm going to give you this mic, Bob. Okay, when you're ready.
Thanks, Matt. Appreciate the opportunity to be here. So today I'd like to give a little introduction to the Martin Fleischmann Memorial Project. So I'm Tyler Van Houwelingen, the Development Director. I'm going to talk a little bit about who, what, where, and then I'm going to turn it over to Bob. So what is MFP all about? Okay, so we have three goals essentially. So the first goal is to show the world that conclusively there is this new practical primary energy source, which we call the new fire. Number two, improve and advance the technology and understanding of the new fire in an open and non-proprietary way so everybody can benefit more rapidly. And number three, we'd actually like to create the foundation of a new type of science, an inclusive type of science, which we call live open science. So why do we need MFMP with Leonardo, Elyon, Elyon? I'm not sure if I said it right, Robert. We've taken a very different approach. Okay, so we've taken a different approach to commercializing Elyon, working in an entirely open fashion, publishing all Elyon information, discoveries, and achievements and techniques to the world. So MFMP can essentially be thought of as the Linux of Elyon. If you take one thing away from us, it's the Linux of Elyon. Just remember that. We believe that the best way to rapidly and comprehensively change the world of energy is to create an open base for the technology to be built upon freely in a collaborative fashion. So we think more openness and social teamwork will lead to better understanding of the effect and broader development of products. So who is MFMP? So MFMP is an international nonprofit collaboration. So you can see the guys here. Everybody's at the conference here today except Julian is not here. From different countries, Europe, United States, Asia, with development labs in France, Switzerland, Minnesota, and California. So again, we're all here today, so grab us if you have any questions, talk to us throughout the week. We welcome the input. But importantly, in the center here is the donors, right? Bob will talk a little bit more about that at the end. We've gotten a lot of donations so far. We can certainly use quite a bit more. But then also contributors and scientists worldwide. So many of you guys in the audience today, many people around the world have already been collaborating with us, have provided us insights, knowledge. We invite you to continue that. Please keep it coming. That's a very important part of the. So you are essentially a piece of the Martin Fleischmann Memorial Project. So there are four phases to what we're doing here. So first of all, we've got the science phase, and I'll talk more about what each of these are. The second one is the validation phase. The third one is the market phase, and the fourth one is the phase where we enhance this together. So phase one, we are finishing phase one right now. So this is the science phase. So the idea, the goal here of phase one is to develop an Elyon experiment and a platform that can conclusively demonstrate excess heat and be used for open global development. So this is the goal here of the first phase. So what do we need to do? So we created a prototype Elyon experiment, which we've done. We've created a scalable network platform to run multiple tests and easily share these results live. And so there's a lot of coding that was done, a website had to be created, databases created, standards developed and chosen. And then we've got separate teams working initially in USA and Europe on this, and we're sharing the information back and forth. So what's the status? So where do we get on phase number one? So based on Professor Chelani's work from ICCF-18, we have built and run multiple prototype Elyon experiments, which Bob will talk quite a bit more about in his second half of the presentation, with live feed and with all the data and design being posted to our website at quantumheat.org. So everything is out there. Nothing is being kept hidden. You can go, you can see the experiments running with real-time data right now. So we invite you to go to the website. So phase two, the validation phase. So what's the goal here? So it's basically to conclusively demonstrate Elyon in a prototype experiment. Are we there yet? We're close. We're not there, but we're close. Differing opinions on the team of what we've seen so far. So the idea here is to create an easy to replicate, easy to measure, with clear, scientifically positive excess power gain. Kind of jumbled that a little bit. But basically, we're trying to conclusively see in a very scientific manner the excess power from the experiment. It's got to be low cost. It's got to be something that's simple to manufacture, simple to replicate, and that it will demonstrate excess heat for about 70% of the people that we give this test to if they try to replicate it. 100% of the time is the goal if we have people qualified testing it in the way we set up. So what's the status here? So we have begun to see hints of excess heat. We're getting about 8 to 12% in kind of the best experiments that we have had so far. And we're hoping to achieve validation and publish robust scientific results in the next couple months. So we believe we're right at the cusp. We think we're close. So phase number 3, okay, the goal is the market. Okay, so the idea here is that we will raise some funds, build and ship a reference Elyon demo dev experiment kit. Okay. So we have preliminary designs for the go-to-market reactor. So currently, today, we're working on prototype reactors. We've done several different experiments, and we've learned quite a bit in the process. And we've got the basic design done now for our go-to-market reactor. And Robert carries around a copy of that design with him at all times. Very proud of it, and he'll show you that. And you can also go check out our table and take a look. But our goal here is to raise about 150 to 320,000 pounds. With a Kickstarter plans with rewards from small things, t-shirt, DVDs, to basically a full Elyon reactor. So when we're on Kickstarter, you'll be able to go there and buy one of our reactors. So there's commercial Elyon. You can buy one. We're also applying for grants with the Mozilla Foundation. And the idea here is that we've got this go-to-market reactor, and our plan is to distribute this to a select number of labs to basically prove the repeatability of these experiments. So what's our status of phase 3? So we will be launching on Kickstarter within the next few months. So please watch for it. We were hoping to be able to announce Kickstarter at the conference, but we're not quite there yet. We have everything almost ready, and we will be up on Kickstarter very soon. So I got a good kick out of the video you showed earlier. So we are going on Kickstarter. Like I said, nearly all prep work is done, and the initial design for the production Elyon reactor has been completed, and here it is. So this is the initial design. When you go on to Kickstarter, this is what you'll be able to buy. You can take a look at the inside. And basically, we've set this up to be, Bob, are you going to talk more about this?
Yeah.
Okay, so I won't get into too much detail. Bob will talk a little bit about what this is and how it's designed. But basically, we designed it to be very low cost, using off-the-shelf components, be very flexible, using either wires or powder, different trigger mechanisms, and to be able to, the testing and the telemetry essentially built into the reactor. So this is what we're going to have up on Kickstarter for you to get by here shortly. So phase 4, the final phase, is basically to enhance this. So our goal is to deliver as many experiments as possible. So ideally over 100 of these, or many, many more, worldwide, and collectively together enhance the design to deliver an open, safe, high-power Elyon reactor. Okay, so we figure if we can get 100 of these out there, hooked up all onto this open database, all onto the internet, with everybody developing and trying new things in parallel, we think we can advance the science very, very fast. So it's a collaborative effort using a highly customizable standard core Elyon reactor that I just showed. You must be willing to share your data results and knowledge across the community. So we're not looking for people to grab this and try to create IP and go. We're looking to basically do an open development on this. Together we can quickly advance the science and the platform. So the status here is we've already received orders for both the prototype Elyon demo dev reactor and the electronics kit. We've inspired replications. I think Bob is going to talk more about that. And this is essentially the new fire. And with that, I'll turn it over to Bob.
Hello. Thanks. Thank you very much for the University of Missouri to give us this opportunity to talk. there's a very large number of people working on this project, and I'll come on to thanking them properly at the end. I worked in the pharmaceutical industry for a number of years, and the advertising industry, and then for 10 years in the finance industry. I've never spent more than 6 months working for somebody who pays me, and I've spent the rest of the time doing stuff that I find that's fun. And after the ICCF-18, I couldn't live with my conscience any longer, and I kind of spent a lot more of my time and quit my finance job. Okay, so we've seen quite a lot of progress in a short space of time. Just talk you through basically what we got here. So in October 2012, that was our first experiment based on Celani wire. We had loading success, very similar to what was described in Celani's paper, but we managed to burn out our wire, which was a little bit depressing. And then our second experiment on the 12th of the 12th of the 12th, at 12 minutes past 12, that was a Californian time thing. We did that live on Google Hangout, and we had anyone able to come in and check what we were doing, as well as seeing the live results published. And we saw some interesting results. The loading had worked previously, but in the actual active run, we saw 6 watts on 48 for about 2 days. And I'm not going to go into the details in this talk because Mathieu Ballat is going to talk through that tomorrow. So we did a little bit more experimentation in late December, and because of the nature of that experiment, it's all described on the web, we could do some calibration and stuff, but we found out that after we took out the active wire, we saw a drop in output of that cell. And then we created 2 different size versions of the cell. In January and February they ran, one had a maker support and some other improvements, and they were in the same environment, and just see how different designs worked. And whilst we had the same loading success, there were various outputs, and at one point it looked like we were seeing 14% or whatever. But this is the one we were most confident with up until the steel and glass cells, which we'll come on to. Okay, so before we actually had our first excess heat, kind of like tentative science, we'd already started dealing with a lot of the issues and complaints and criticisms of Celani's clear cell design. And some of those we discussed this morning about the Langmuir effect. There's things like variation between pressure and conductivity, conduction, and also things like IR emission from the cell, and the changing in IR absorption of the glass or whatever over a period of time. There was lots of complaints, and we started thinking about how we could deal with a number of these complaints with something that was very simple. We came up with a design which is basically a single-ended Celani cell inside a steel outer chamber. And we can control the atmosphere between the glass and the steel so that we can make it variably conductive, and we can also make it inert or so on. So we've got a lot of things we can do with that cell. And we wanted to have an experiment really that an 8-year-old could understand, and we don't have to explain about super duper calorimetry and this sort of nonsense, because I'm a graphic designer, so I need to understand these things if I'm going to talk about them. So essentially, we've got 2 water buckets here, some insulation, and we've got a stirrer here, which you can see there and there. Same volume of water, and what we're trying to target is the same isothermal temperature of that water, the same evaporation off the top, and see what the difference in power input after loading it would take to maintain the water at the same temperature. What is the MFMP about? It's real science, open and inclusive to all. So what we saw last year was some absolutely brilliant work done by some brilliant minds over a period of time, but it really wasn't getting a wider market. And so how do you get more people interested in that? And so, we're publishing, this is some excellent SEM work done by Mathieu. These things inspire the public, So there was questions about hotspots where the Captain tape or whatever it was that was supporting our thermocouples were, and so that's what's going on there. This here is the end results from the steel and glass cells run in May. And this is after about, 2 weeks?
3 weeks.
3 weeks of attempting to get to an isothermal state between the two cells. You can see from about this point onwards, we've got kind of about the same temperature for the two water buckets. The yellow line is the active cells water bucket temperature, and you've got the input here for the active cell, and this is the input for the passive cell. So for about 2.5 days, it's between 8.3 and 10% more power required into the passive cell in order to achieve the same water temperature. It's really, really easy for people to understand. And, I'd like to see some calculations done by, you can go on our website, you can look at the logbook, you can look at the time slice on the data repository, pull out the CSV, and you can do your own analysis on that. And we'd love someone to say, how much could this amount of Celani wire store, disassociated energy of split hydrogen, and then say how much the Langmuir effect would cause after the loading process when it reassociates on the glass. And then once we've gone to steady state for a while, maybe we can have a discussion about what kind of net cumulative energy gain we're having. Okay, so we're not willing to just stop there, and Paul's a bit of a genius, and he's been very good at supporting the project, and he's created this, one of his creations, a concentric calorimeter, it's airflow calorimeter, and right now this is running a live experiment. You can see there's 50 meters of untreated Constantan wire, because we wanted to up the signal to noise ratio, but we want to start with something which is not Celani wire and see what we see, and we don't see a lot. We maybe see a lot of loading going into the wire. We're not entirely certain about that. We need to look at it afterwards, but it's right there now. You can go on the website and you can see the live data being produced from that. So nothing interesting, non-treated wire. Draw your own conclusions. The cell can go up to 10 bar, 500 degrees C. Okay, I'm just going to move it quickly. So this is, Celani came with us in February and said, I'm doing a new protocol, which I think he's going to talk about. It's a vacuum protocol, but we thought we're not just happy now with doing one cell and having to do all the calibration and stuff. We'll do 2 cells and have a differential. They're exactly the same in every way, apart from this cell here. One of the cells is loaded, and then we do our active run. And actually, in the European cell, Matthew has beaten himself up about this, and probably there was a delamination of the thermocouple, so we had to kill this experiment. There wasn't any time to rerun the calibrations prior to ICCF-18. But in the US cell here, where they've got some sort of active cooling going on, it's live right now. I don't know if it's actually on an active run right now, but we've seen something near 4% in the potential excess there, and over 95% confidence interval. Again, Matthew's going to go into the details there. But we're cycling this over and over again, and if anyone's got any better ideas about the protocol we should be using and challenge it, then we'd love to hear it. Okay. Some other things we've been doing. Matthew helped John Paul Bavarian produce this cell here, and we restarted some powder experiments, but it's what some of the group are doing over and above the Celani work. Okay, so this cell you made, is it on the stand? The water flow calorimeter?
That one's in the lab.
Okay, that one's in the lab. What we're going to do with this just after ICCF-18 is we're going to put 3.5 meters of active wire in there. It's the most that any reactor's ever had in it. And we're going to try and load it, and it can go again to sort of 500 degrees and high pressures. So we've got a lot of flexibility of what we can do. So some exciting research to come out of that. Keep a looking at the live data streams. Okay, so live open science. You've seen our poster, hopefully. If you need to talk to us about it, let us know. We're inspiring new hardware and software. We've had an infrared camera software being made for us. That's going to be published and made open source, being converted to Linux. A groundbreaking hardware data visualizer, and we're going to make an open source version of that, and control and monitoring hardware and software, and we're working towards making an open version of that. So momentum, why don't you jump on board? Right now we've got 4 new teams on 4 continents poised to join our collaborative effort. So what might happen in the near future, we're going to have a doubling of the effort going on, and the most important one of those is Queensland University of Technology, and we're really pleased because they've got a lot of equipment, way more than we've got combined probably. Skilled new team members are joining all the time and asking to join. Increased interest for people asking for equipment, as Tyler suggested. And this is Dr. Sinha Bark, and he said basically if we have something to test, they're willing to test it. Okay, I just want to quickly say thank you to Chelani for his incredible courage and his humility.
Thank you, Professor.
It took an amazing amount of guts in order to be able to go forward with that. I want to say thank you to our donors, our followers, the facilitating team for their sacrifices, the large number of scientists both inside and outside this group that have given their time and advice, National Instruments for a very significant contribution, and Hunt Utility Groups for an incredible amount of resources they put towards the project. How can you help? Suggest, criticize, give time, give capital. If you've got any money, there's a huge social multiplier. $1 in produces a hell of a lot of work.